Hi, this is lesson 2.2, the product rule. The goal of today's lesson is to learn the product rule of taking derivatives. This will allow us to take the derivatives of more complicated functions where we have two functions that are multiplied together without having to expand them all out first. Okay, so let's start out by taking the derivative of this first example, y equals 3x to the power 4 plus 2x cubed. Pause the video please and go ahead and do that. So by using the power rule, we see that dy by dx is 12x cubed plus 6x squared. Okay, so in the last section we realized that the derivative of the sum or difference of two functions was the same as the sum or difference of the derivatives of the two functions. So now we're going to take a look at something a little bit different here. So if we want to take a look at the function h of x, which is 100x to the power 5, as a product of two functions f of x and g of x, where f of x is 2x squared and g of x is 5x cubed, we want to take the derivative of the product of the function, or determine if the product of the functions is equal to the product of the derivatives. So when h of x equals f of x times g of x, we've got 20x squared times 5x cubed. Therefore, h of x equals 100x to the power 5. So what we're going to do is we're going to take the derivative of h of x. So we've got h prime of x, and that equals 500x to the power 4. If we were to take the derivative of f of x and g of x independently and then multiply them, we would see that we get the derivative of f of x gives you 40x, and the derivative of g of x gives us 15x squared, and then when we multiply them together we see we get 600x cubed, which is not the same as the derivative of h of x. So if h of x equals f of x times g of x, then h prime of x does not equal f prime of x times g prime of x. Okay, so even though the sums and differences that we saw yesterday, the derivative of the sums and differences was the same as the sums and differences of the derivatives, it doesn't work the same way with multiplication. So, quite conveniently, some brilliant mathematician way back when came up with a product rule to help us out with this burning dilemma. So if we have some function capital P of x equals f of x times g of x, where both f of x and g of x are differentiable, i.e. there are no cusps or corners or holes or vertical asymptotes, then P prime of x equals f prime of x times g of x plus f of x times g prime of x. So basically, the derivative of the first times the second plus the first times the derivative of the second. In Leibniz notation, the derivative of p of x with respect to x is the derivative of f of x with respect to x times g of x plus f of x times the derivative of g of x with respect to x. Alright, let's prove this, shall we? So we'll prove this by using the first principle, so the limit definition of the derivative. So uppercase p prime of x is the limit of uppercase p of x plus h minus uppercase p of x all over h as h approaches 0. And we know that p of x was f of x times g of x. So this p of x gets replaced by f of x times g of x, and p of x plus h is f of x plus h times g of x plus h, because we're just replacing that with f of x times g of x, but we're replacing x with x plus h in both cases. Then what we're going to do is something very, very sneaky, and on the next line here we've got f of x plus h, g of x plus h, and this part, f of x, g of x, is over here. In the middle, what we've done is we're adding 0. Negative f of x plus h, g of x, plus f of x plus h, g of x. So we've got the sum and the difference of the same term, so we're actually just adding 0 into this whole fray, and that's quite convenient. We can do that no problem, because we can add 0 to whatever we want and we're not changing anything. So now this will allow us to do a little bit of factoring and simplify down to what we need. So then this is going to equal the limit, and we see in these first two terms, what are we going to do here? We're going to let's factor out the f of x plus h here. So we take these two terms and we'll factor out f of x plus h, and that leaves us g of x plus h minus g of x, again all over h, and then now we're going to add, and this is all in square brackets here, now we're going to factor out g of x from this, g of x, and then that leaves us with f of x plus h minus f of x all over h. Now that we factor that out, we've got basically two functions in each term. We've got two functions multiplied together, and with limit definition, the limit rules that we saw in chapter 1, we'll take the limit of each of those things independently. And now we'll just take a look at these different parts now, and we see that this is the limit definition of a derivative of g of x. This is the limit definition of the derivative of f of x, and then we just apply these zeros to these. So if you substitute 0 into this, what are we left with? F of x. And when we substitute in h or 0 into here, that's the limit definition of the derivative, so that just leaves us with g prime of x. And then over here, nothing changes there, because when you substitute h in, or 0 into h here, there's no h's, so that just leaves us with g of x, and this over here is the limit definition of the derivative of f of x, so that gives us f prime of x. And then now we just change this around to get it into the form of the derivative of the first times the second, so we're just switching these two, the order around here, plus the first times the derivative of the second. So that is the derivative of a product of two functions. So the derivative of the first times the second plus the first times the derivative of the second.